Hello guys, intermolecular forces today. But before I talk about intermolecular forces, I have to talk about forces between particles in general in chemistry. So I'm just reminding you what we are dealing with here. Not going deep into philosophical side of the story, everything is made of particles, and by particles we define the things in which the object falls apart if we shake it strong enough. You see, if we shake the matter strong enough, like in Hadron Collider, it would break into protons and neutrons and electrons and even quarks, though they are not separable from each other, so there will be bunches of elementary particles. Well, that's not our business in chemistry. When we shake matter in chemistry pretty moderately, we just heat it up and it shakes itself, because temperature is the random thermal motion of particles. So here we are dealing with questions of melting, questions of boiling, question of enthalpies of fusion, energy needed to melt 1 mole of a substance, or enthalpy of vaporization. Obviously, enthalpy needed to vaporize 1 mole of the substance. So these enthalpies would depend on the energy connecting particles together. What are these forces keeping matter together, which we are talking about? Keeping molecular substances together, or keeping any chemical substance together, because we can melt metal, we can melt ionic substance, we can melt giant covalent substance, even we can melt molecular one. So are all these forces different, or is there something similar in all of them? There is something similar in all of them. All of them by nature are electromagnetic. All of them by nature are, even in simplification which we use normally here, electrostatic. So it's a force of attraction or repulsion between charges being at certain distance. And what is the bond? What is actually the force keeping particles together? Either atoms in the molecule or molecules in a solid state. What is the bond? Bond is some force of attraction first, and bond, more essentially, is the energy you have to give to the particles to overcome this attraction. So what this energy depends upon? Here is a simple dependence. There's simple formula showing the energy of interaction between particles, between two charges. So there is charge 1, there is charge 2, Q1, Q2, one is positive, another is negative, they do attract each other. How do they attract each other? There is Coulomb's law showing that the force of attraction is proportional to the charges themselves. The bigger the charge, the bigger the force. And it's inversely proportional to square of the distance between them. So if I increase the distance 10 times, the force would drop down 100 times. Well, but we are not so much interested in the force. We are rather interested in energy of interaction between particles. The energy of interaction between two charged particles is inversely proportional to the distance. Here I written energy is proportional to distance between them to power -1, and proportional to the charges themselves. Yeah, clear? The bigger the charges, the bigger the energy of interaction. Charges are bigger 2 times, each of them. The energy is bigger 4 times, because I multiply the charges. Distance is bigger 2 times, the energy is smaller 2 times, because it's inversely proportional. So now, this is the essential thing in all interactions in chemistry. It's interactions between charges. But not all charges are as simple as this, just plus and minus. Sometimes they are more complicated. They can be dipoles, separated a little bit in space, partial negative and positive charges, which go always together, part of neutral complex. Or they can be totally even neutral things which would interact, dispersion forces. So let's talk about interaction between particles in chemistry in general. So here I have a table where I attempted to make a list of all electrostatic, essentially, interactions, bonds, which keep the matter together. So obviously here is three main types of bonding: ionic, covalent, metallic. Ionic is very similar to the simplest case we look at. Clear, separate charges interacting with each other. Always pluses are surrounded by minuses, minuses are surrounded by pluses. Energy of interaction is total energy experienced by the charges in crystallic lattice. Energy needed to be given to the charges, to the ions, to get them out. So, or covalent bonding. Yeah, that's pure attraction between plus and minus. Covalent bonding. It's a bit more complicated. It's attraction between shared pair of electrons and the nuclei of the atom. But it's still attraction between plus and minus. Again, the bigger the charges, for example, there is two pairs of electrons, yeah? And the smaller the distance, the stronger the attraction. It is always the case. Bigger the charge, smaller the distance, stronger the attraction. So if the atoms have smaller radius, if they have double bond or triple bond, the force of attraction would be stronger. The bond would be stronger, total. Then there is a metallic. Even also a little bit more complicated, but essentially the same. It's always pluses to minuses, minuses to pluses, attracted. Just how they are generated, that's the difference, and that's the question here. So in metal, as you know, there are delocalized electrons flowing in the lattice made by positive metallic ions. So metal atoms, when they join to form metal solid, they would lose their outer valence electrons, outmost electrons, and they would be delocalized, common one, and be able to move freely inside the crystal. And so this negative cloud of electrons is attracting positive ions, which are composing the crystallic lattice. So these are the main forces, the main chemical bonds which you know about. So very simplistically again, what can we say about them? So ionic bond is a bond between metal and non-metal, normally, like chlorine and sodium. Covalent, it's when electrons are shared. Covalent be still polar, so electron pairs shifted to one of the atoms, more electronegative, but it's not totally given to one of the atoms. Yeah? Then the metallic bond is just between metals. So either it's a metal element or a mixture of metals, which you call alloy. So again, yeah, what I'm emphasizing here, interactions, chemical bonds, even between atoms, because these are different bonds between atoms. That's how they established it. So they are still based on the same law, on the same principle of attraction between charges at a certain distance. And the bigger the charges, the smaller the distance, the bigger the energy of attraction, the stronger the bond. So here I put the relative strength of the bond. Let's say it's 1, yeah? Obviously metallic bonds can be very strong, like in, say, case of iron, or rather weak, like in case of sodium. Look at the melting points, yeah? But on average, in general, very simplifying, we say they're about the same order. Let's say it's strength 1. Then there are a bit weaker forces, and here all of them, there are 3 of them, they are all intermolecular, between molecules. These are between atoms composing something, and covalent bonds, it's a group of atoms joined together by covalent bonds, would compose molecules. Now, covalent bonds are rather strong. When we melt molecular substance, we break some other bonds, intermolecular. And here is the list of possibilities which they have to overcome. So, what type of intermolecular bonds are there? So, here I ordered them strength-wise. So, the strongest are hydrogen bonds. So if hydrogen bond is established, in small molecule at least, it would define the property of the substance. So water is totally defined by its ability to form hydrogen bonds between molecules, and even like 4 hydrogen bonds per each molecule. What is the condition for existence of hydrogen bonds? There should be either fluorine or nitrogen or oxygen with hydrogen bonded to them. So OH group is in the molecule, it would establish hydrogen bonds. NH2 group, amino group, is in the molecule, it can establish hydrogen bonds. Or there is FH, it's just hydrogen fluoride. It cannot be part of any molecule to fulfill the condition, because fluorine forms only one bond, so it can bond only to hydrogen but not to anything else. So hydrogen fluoride would still be able to form hydrogen bonds. So hydrogen bonds play a huge role in life, in chemistry, in arrangement of proteins. But I said everything in chemistry depends on interaction between some charges. So where are the charges here? Well, I just didn't draw them explicitly. We know that oxygen is a very highly electronegative atom. So the bonds between hydrogen and oxygen would be polar and electron density drawn to the oxygen side. So delta minus excessive electron density on oxygen on its lone pairs. And here in the neighboring molecule, what happened to hydrogen? He's losing electrons to oxygen. And hydrogen bond by itself, what is it? Is an attraction of polarized hydrogen of one molecule to the lone pair on small highly electronegative atom. Why highly electronegative? It has to concentrate a partial negative charge on itself. Why small? Because the lone pair, the smaller the lone pair is, the highly concentrated charge on it also. Why hydrogen is needed? Hydrogen is the only atom, okay, except for helium, which doesn't have inner electron shells. So when electron density is withdrawn from it, it's basically bare proton, and proton is 100,000 times smaller than average atom. So it's depending on amount of electron density drawn away from hydrogen, it can get extremely small. So, and you see, the closer the charges are together, even they are small charges, yeah, relatively, it's not +1, it's a fraction of 1, it's not -1, it's a fraction. Still, they can come extremely close, because this is basically a proton and this is small negative pair of electrons. Attraction between this is exceptionally strong, force of attraction between molecules, on average 10 times smaller than, say, covalent ionic or metallic bond. It's significant, but still, when we boil water, these bonds would break, not covalent ones, because these are weaker. So what will be the particles? Not hydrogens and oxygens, but water molecules, H2Os, would separate from each other. Okay, what can be second case? The molecules still can be polarized, but maybe there wouldn't be an ability for them to form hydrogen bonds, because hydrogen bonds is limited to this case. You need, just generally, practically, nitrogen or oxygen and hydrogen atom bonded to them. If structure of molecule doesn't have that, like hydrogen chloride, for example, no hydrogen bonds for them. So what they rely upon? Dipole-dipole interactions. That's the next strongest force between molecules, at least between small ones again. So because here is still partial charge formed on the atoms, so here partial positive charge on hydrogen, partial negative charge on chlorine. Again, why? Look at the tables. Electronegativity of chlorine is bigger than that of hydrogen. Electron density or the bonding pair would be withdrawn to chlorine, giving it some negative charge. generating therefore positive charge on hydrogen. So molecules should orient in particular way so that positive end of a molecule is facing the negative end of neighboring molecule. This is possible, yeah, if you add a little bit more of them, minus plus, yeah, plus minus, sorry, yeah, okay. These forces between permanent partial charges would keep the substance together. At least there is clear charge, yeah? Not as strong, and they cannot come as close together as in hydrogen bonds, but quite significantly strong. Okay, I've written there about 150 of average interatomic bond, and about significantly weaker than hydrogen bonds. Now, the last case of intermolecular forces, and also in a sense the most important. It's the weakest, and it's the most puzzling of them, because now we have to have an interaction between molecules which are not polar, which don't have any part which is partly positive, another part which is partly negative, and they can interact, like in example above. And what is the condition, by the way, to example above? Here I've written the conditions. First, the bonds in the molecule should be polar, and second, the molecule should be not symmetrical. If the bonds are polar and the molecule is symmetrical, no dipole can be formed. Because you see, say there would be negative charges, and here would be positive charge in the center, say in carbon dioxide. Yeah? Carbon dioxide is linear, negative oxygens are here, positive carbon is here. For dipole, it's di2 pole polarity charges. It's a charges plus minus. We simplify them as point-like charges at certain distance. The bigger the charges, the smaller the distance, the stronger the dipole. So, but the molecule itself should be dipole, not the bond only. So if you have symmetrical distribution of bonds, dipoles cancel. So you have something non-symmetrical, like pyramidal, band, something like that, V-shaped, seesaw-shaped. These molecules would be polar. They shouldn't be symmetrical. Okay, there are always conditions, you see. These intermolecular forces are conditioned on something. These are strong but rare. Okay, very common in organic chemistry and living matter, but relatively rare. You need particular conditions to be fulfilled. Here, still some conditions are needed. The last ones, they always work. It's a forces which always exist between molecules. There are hydrogen bonds, dispersion forces still would exist. There is dipole-dipole interaction, dispersion forces still exist. So we call them dispersion forces or London forces. These are the forces between neutral, non-polar molecules, like between alkanes. What they depend upon and how they ever happen. So here I try to show the forces generated between, say, two argon atoms. Noble gases, they don't form any chemical bonding. So it was a puzzlement when in the beginning of 20th century it was discovered that noble gases can actually be liquefied. What are the bonds keeping them together? There is no charges. The atom is purely symmetrical. There is no dipole of any kind. How they can be kept together? What is the force preventing them to separate? It was discovered, theoretical background for that at least was provided somewhere in 1930. One of the people working on that was London, that's why the force bears his name. And the essence of the force is quantum mechanical. Well, we know that electrons are not really particles which swirling together around the atoms. They are, we say, electron clouds rather. They are rather waves There are standing waves around atoms which are stable. These are electron clouds. It's not swirling of anything around a negative charge around the positive one. So pretty often, even in university books, they explain it a way kind of saying that, okay, you know, electrons, they're turning around the atom, and sometimes they generate on one side of the atom, and therefore this side is negative and another side is positive. Well, that's not that's a very feasible explanation, but it's nothing to do with reality. Reality is different here. We are facing blankly quantum mechanical reality, where particles are becoming really waves, and where uncertainty principle, impossibility to know at the same time position and momentum of particle, for example, is becoming very important. So here are what we call zero oscillation of fields, which are creating this. Yeah, I better stick to electrons whirling around the atom, at least it's understandable. Well, this thing is not very understandable, I admit, but there are electron clouds in the molecules, and they intrinsically, essentially oscillate. You cannot say with certainty what would be the density of the cloud at any point, at any time. So we don't have a certainty, there is a possibility of distribution. On average, negative charge is distributed symmetrically around the nucleus. But in any particular instant, moment, the distribution would be different. So if in one of the molecules, or in one of argon atoms for that matter, distribution is instantaneously at particular given moment is on one side, it can induce redistribution of electron density on neighboring atom. Induced instantaneous dipoles are generated. Induced polarity on one molecular atom is forcing polarity on another atom. You see here partial positive charge because electron density is shifted here. Therefore, electrons in the neighboring molecule are attracted to this partial positive charge. This partial positive charge is fleeting, and this dipole-dipole interaction is momentary. Induced random events in one of the molecules are affecting events on neighboring molecule. Instantaneous distribution of charges are constantly changing. It's not fixed like in polar molecules. So, but still they would interact with each other because partial positive-negative charges are formed in the molecule, and they're always in tune because they're induced, So if there is plus, then there would be minus in the neighboring molecule. And there would be a force of attraction between them. Now, what this force of attraction would depend upon? As usual, the stronger the charge, the smaller the distance, the stronger the force. So here, with London forces or dispersion forces, when they're going to be bigger. First, when simply we have a higher polarizability of electron cloud. So, for example, bigger atoms would have stronger forces of attraction, if you talk about noble gases, than small atoms, because outer electrons are farther away from the nucleus and can be easier polarized. But what is the more certain way to talk about to talk about dispersion forces? Just simple way, calculate number of electrons in the molecule. The higher the number of electrons, the stronger would be the induced instantaneous dipoles, and therefore the stronger would be the dispersion forces. The second thing, the molecules should be really close together, because the force, the energy of interaction dies away very strongly when the molecules are coming away. So if the molecule is branched, the dispersion forces wouldn't be that strong. Because you see, the atoms should be close together, neighboring atoms in neighboring molecules, to interact. So, for example, this type of molecule would have a much better chance to form induced dipoles between neighboring atoms than this type of molecule. Yeah, this is butane, yeah, and this also have 4 carbon atoms, but they cannot come very close together because they are branched. So, okay, surface area of contact also has a role. So, spherical molecule, well, atom, say, of noble gas, and say a bit linear molecule, say of chlorine, yeah, compared to, say, krypton. Chlorine is elongated and can provide bigger area of contact between molecules, therefore stronger dispersion forces, even if number of electrons is the same. So here again, the more electrons, the stronger the dispersion forces, and the bigger the surface area of contact between molecules, the stronger the dispersion forces. And there is another special thing about dispersion forces. They have no conditions for existence. They are always there. As soon as you have atoms with electrons around, dispersion forces would be there. They are tiny, yes, but in huge molecules they add up, because each group of atoms in the molecule establish these forces between them and neighboring groups of atoms in another molecule. The longer the molecule, the stronger the dispersion force. It can become, on addition, as strong as any of this. Well, not that maybe strong, yeah? You wouldn't get melting point of molecular substance probably of 1000 degrees, but it can be a few hundred degrees melting point easily. So, another few words to add about it. I want to talk a little about the dependence on distance. So what this section is about? It's how forces of interaction between particles depend upon the distance between them. I said already, yeah, like in clear charges, or when you separate ions in ionic crystal from each other, you would overcome the force of attraction. The energy of attraction is proportional just to the 1 over the distance in power of 1. Inversely proportional to the distance. Distance increases 2 times, energy of interaction drops 2 times. What about dipoles? Dipoles, you see, they go together. Where there is plus, there is minus also. So you see, this plus and minus, they attract each other. But these 2 minuses, they repel. And these 2 pluses, they do repel. So, and also another thing, when you separate dipoles from each other, kind of look at the scale drawing here, yeah? They're becoming tinier, 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 and plus and minuses would look from the distance very close to each other. So their effects would cancel. So the force between dipoles dies away very strongly with the distance. If the distance is increased 10 times, the force would drop 1000 times. It's 1 over r to power 3. What about dispersion forces? You see, dispersion forces, they are made of induced dipoles, which are not permanent, which are fleetingly existent and constantly changing around the crystal. And if I separate molecules from each other, they wouldn't induce dipoles on each other. So the force between molecules here, dispersion 1, London force, would drop down even stronger than r to power minus 3, like distance to power minus 6. So if I increase the distance 10 times, the force drops a million times. So the force really is very sensitive. The molecules should be very close together for this one to exist. So here is what I can say. Another revision. Well, I would remove this. Again, what do we have? All forces keeping particles together in chemistry is forces of attraction between positive and negative charges. So there can be forces just between atoms. They can be ionic, covalent, metallic. They are relatively strong. Then some atoms form closed groups strongly connected to each other by covalent bonds. We call these groups molecules. Now, when you melt molecular substance, you have to separate molecules from each other, this group of atoms, because forces between molecules are much weaker than forces between atoms in the molecule. You see, like 10 or 100 times weaker. So what are intermolecular forces? First, there are dispersion forces. Just on the very fact that molecules have electrons and have some geometrical shape, these forces would be there. The bigger the number of electrons, the bigger the surface area of contact. Say linear molecules have stronger interaction between each other than branched molecules with the same number of electrons. So the bigger the number of electrons, the bigger the contact between neighboring molecules, the stronger the dispersion force would be. So yeah, my name is you see, it's induced instantaneous dipoles attraction. That's the essence of it. Also it has a name dispersion force. Also it has a name London force. The same thing. These things sometimes are generally called van der Waals forces. Just van der Waals forces, very loosely, is used to describe all forces between molecules. So intermolecular forces equals to van der Waals forces. Yep. The strongest, the next most important van der Waals force or intermolecular force is hydrogen bond. Because it's really the strongest of them all, and for small molecule, obviously it wouldn't matter much if there is 1000 carbon atom chain and just one OH group on the end. But for small molecules such as ethanol, these hydrogen bonds would be totally defining their properties. So hydrogen bonds are very strong, needed for that strong small electronegative atom connected to hydrogen should be part of their structure. Then dipole-dipole forces, which sometimes, when everything else is equal, would really define the melting point, would affect. But their effect is relatively small. They are not very strong and they are not additive as dispersion forces. Dispersion forces would strongly, slowly dispersion forces and dipole-dipole interactions, permanent dipole-dipole interactions, are not additive. You see, if you increase the size of molecule, they are not growing bigger. But these ones will. They just depend on the size of a molecule because they depend on the number of electrons and the surface area of contact. They are additive, they are very important, these ones are very important, these can play helper role if everything is the same. No hydrogen bonds, number of electrons is the same, the substance which is polar will have stronger interaction between molecules. Otherwise, it's pretty secondary importance. These two are the main. Well, that's what I wanted to tell you. I hope it's clarified a little bit. If not, ask me questions. Ask me what really is the puzzlement, because I know that this thing is really puzzling for people. It's pretty clear when you look at it from the point of view of physics. Sometimes just broken in so much details, but you always have to remember its interaction between charges. the only thing which determines the bond, how strong the charges are and how close together they can be. Thank you, see you next time, subscribe to the channel.